and welcome back to this lecture series on cyber physical systems. So, in the last lecture we discussed about Lyapunov functions and stability. So, in this lecture we will be talking about this new concept called barrier functions. So, this is a method to kind of reason about the safety of such autonomous systems. So, let us first understand the basics of safety. I believe we also discussed about safety when we did hybrid automata based modeling of systems and reachability. So, suppose you have a continuous time system like this, and for this system you have this equation x dot equal to f x of t, and x t is belonging to this domain D. Now, this system has initial set of states, let that be x 0, and it is safe if let us say that is safe, right. But the question is, when do I say that this system is safe? There should be some notion of unsafe also. So, let us say that inside this domain on which the system is defined, there is another set u. So, u is more like a subset. So, this is not belong to, this is a subset symbol here. Okay. So, you have a subset of D, which we call the set of unsafe states. That means, it may or may not be possible for the system that even once because it is autonomous, it will be moving around, it will be changing its location in the state space. So, it may or may not get into those set of states which are in U, right. And we say that, well, that is unsafe because they may be they may be hazardous for the operation of the system. Okay. Now, the question is, how do I define the system to be safe? So, what we say that, well, let the system start in a set of initial states given by x naught. That means, it is a set of initial states. That means, it can start anywhere inside because x naught, because all these are is in a continuous space, right. So, x naught is also a set containing an infinite number of possible initial states of the system, and we say that, well, this is the set of safe initial states provided as long as the system starts from this from any state which is included in x naught, there does not exist any future time instant t such that x at t will be a point located inside U. So, let us understand what we are doing. We are defining something in your state space as unsafe. So, we picked up, let us say, so this is your domain, and then let us say we said that, well, this is a region which I want to avoid. Then what is my set of safe initial states? We will say that this is my set of safe initial states as long as if I can start from anywhere here. So, let us say this point x is where I am at t naught, okay, initial time. I have a guarantee that in future, at no point in future, I should land up inside U. Okay. So, as long as I have a set x naught, so that I can start from anywhere inside this set, and in future there is no time point when I land up in U, I will say that this set of initial states is safe. Okay. So, an unsafe region is something which will satisfy some given unsafe property of the system. So, there will be some definition. Let us say for a vehicle, this air to fuel ratio is bad, right. So, that is an unsafe region in the state space. The vehicle's controller should be designed in such a way that overall it never happens that you get to that kind of air to fuel ratio, something like that. Okay. Now, the safety property is actually a stricter property and harder to verify, and it needs to be verified for all possible timestamps and all possible initial states. So, that is an important thing. You see, we are talking about that, well, we will say that this is safe if I can show that I can start from anywhere inside this, and starting from anywhere inside this, in future wherever I go, I never land up in U, right. So, it needs to be verified for all possible timestamps and all possible initial states, right. So, that is the problem for all possible x naughts in this capital X naught and all possible values of t which is greater than 0, right. So, in reachability based verification or the SMT solvers, we need to search this reachable space which contains such an uncountable infinite state space, and then the question is, how do I deal with that? So, we will like to have some analytical method for proving that some system is safe indeed, and it will never get inside an unsafe region. One such method is what we call as barrier certificate. So, let us understand what is a barrier certificate. It is a very simple thing. If you have understood Lyapunov function, it is just like an extension of that. So, this is also a continuously differentiable function mapping to a scalar value in the reals. Okay. So, what it does is you have certain properties of this function which have to be true. The first property is for all elements in the initial set of states, this function must be negative or 0. So, for all x which is inside the set of initial values, Vx is negative, and for all x which is inside that unsafe set of states, Bx must be positive. So, notice the trick. You are given a system and you are given the set of initial states and you are given the set of unsafe states, let us say using some closed form expression. Now, your job is to find a function which is negative for any point which is there inside this initial set of states, and it is positive anywhere inside this set of unsafe states. And apart from this, for all other positions, apart from this, in general, for all points in this domain of the system, the derivative, the time derivative of this function is negative. So, you can see that it is something just like the Lyapunov function. But with some differences, there is a notion of unsafe state where the function is going to change its sign, otherwise the function is negative, and the time derivative of the function, if you take time derivative of b, it is basically the space derivative of b times the time derivative of x, which is f x, right. So, the time derivative of b is negative everywhere in the state space, right. So, if you can find such a function, then you can have a guarantee that every trajectory of the system dynamics which will start from x naught. So, that is the trick. The trick is in finding the function, and then you can claim that, well, I have found a function such that see this function, if I am able to initialize my system inside x naught, this function is negative by definition, and everywhere inside the state space, the rate of change of this function with respect to time, that is negative, right. So, it is a decreasing function. That means, if it is initially negative and it is a decreasing function, it is not possible for this function to ever be positive, and hence I will conclude that since it cannot ever be positive, it will my system, that means my system trajectory is never going inside u, because if my system trajectory has gone inside u, then Bx would have been positive, but if I can figure out the function in such a nice way that it satisfies point 1 and it satisfies point 3, then I see that, well, there is no scope of the function to ever be positive, and so the system, I can say, will never actually move inside you. Okay. So, there is a trick to find out a function which will satisfy all these quantities. If we can figure out that function, then we can clearly say that all trajectories of the system dynamics which start from x naught, they will not reach the unsafe region. That means, in a way we can say that the safety specification is respected. So, this is called a barrier certificate or barrier function for the system. So, suppose you are given a system and it has a complex algebraic formulation or something like that, and you are told that, well, you proved that this is a safe system and this is my unsafe set of states, and can you show that this will never, my system will never go into that unsafe state. If you can design a function like this, okay, then it is like a certificate which is telling that, well, you see, since I have found this function which satisfies all these requirements, this system that you are talking about will never go into the unsafe state. Now, again, just like Lyapunov function, you need to understand the link between this function and the system. So, the link is again by this, that when we say time derivative of b, it becomes the space derivative of b times x dot, and that is f x. That means, the function is defined over x and x is changing position with time. That means, you are practically evaluating the function only on the trajectory of the system x dot equal to f x. X dot equal to f x is a trajectory which is changing x with time, and you are always evaluating the function on this trajectory. As long as this function satisfies this requirement, you are starting with the function being negative, and its rate of change is negative. So, the function will remain negative, and that means in a way, since the function's evaluation is on the trajectory will never move into u, because had the trajectory of the system moved into u, since you are evaluating the function over time again and again, and you are now going to evaluate it in such a position where the function will be positive. Okay. But as long as that does not happen, if you meet 1 and 2, then well, your system does not really go into the set of unsafe states. So, that is a nice elegant theorem which defines Verrier function. Now, let us prove that well, why this should happen, why I can claim that I think the idea is very intuitive, but again we can give a formal proof. The claim is that well, if this function exists, then the system is safe. So, let us try. So, we will try this proof by contradiction. So, we will assume that such a trajectory exists for which the system can indeed start in this state of initial states, and the system will veer into an unsafe state. So, it will start at x naught and eventually reach this u. At some time t c. So, let us say at time t naught I am at x naught, which is inside this. Okay. So, that means the function b at x naught, right, it is negative, because x naught belongs to this capital X naught initial state, right. But say I reach u at time t, then b at this time t is positive, right, because x t is a member of the unsafe state u, unsafe set of states u, right. So, that means see b is a continuous function, right. If you look at our definition, these are continuously differentiable function. So, you have safe and you have unsafe, right, and let us say you are unsafe. So, if you are moving like this, there must be a position here where you cross it over, and if you see, we are saying that well, when I started I was negative, and then suddenly when I reached here I became positive, and here I was negative. So, that means there is some position somewhere here, right, somewhere here where b is equal to 0. This moves to b greater than 0, that means there exists some position where so, let us say this was my initial point, right, this is t naught, and this is t. So, there exists some tau, right, which is a member of this interval t naught to t, okay, and we can say that b at x of tau, that is equal to 0. So, that is where the function becomes 0 and then become positive, right. So, we consider two cases. tau is greater than this initial point, some point here, and let us compute this integral. So, this is like if you see this thing, this is nothing but a time derivative of b, right, because it is equal to space derivative of b times x dot, which is f x t, right. So, I can always write this as where t is evaluated at 0 at tau. Now, at tau I have said that b is 0. So, minus b at x t naught, right. Now, we know that this is less than or equal to 0, right. So, we will have this as positive, but this in that case is kind of contradicting the third condition, right. Because if you see, the third condition says that the integrand, which is this, the integrand is always negative for all positions in the domain. So, for all x in the domain, we have that b dot, which is given by del b del x into f, that is this, right. So, that is the third condition. Now, if this third condition is true, then this integral has to be negative, but what we get is positive, right. So, this is like a contradiction. Now, there can be one condition, which is that the initial state is at the boundary of the certificate itself. Okay. That means you have, because if you see that you may have a question that, well, we had this, right. Let us see, this is b x is less than or equal to 0, right, and then it became positive inside, and somewhere in between it has been 0, right. So, now let us consider this condition, that let us assume the initial state is not outside, not properly outside this unsafe region, but it is somewhere here only at the boundary. Okay. So, and why is this important? Let us understand. Earlier we said it is here, and we went into here, where inside, once I get inside, it has to be, b will become positive. That means somewhere in between it became 0. Now, let us say that, well, it may happen that it becomes 0 right on the boundary. Okay. So, if I mean it may, I mean this equation also holds in the boundary situation, that, well, x does not start outside, but x starts in the boundary itself. Okay. So, this is your position at initial time. Okay. So, suppose that is the situation. Now, if that is true, then b of x t naught, or let us say this is called x naught, this itself is 0. I mean, it is not negative or less than or equal to 0, this itself has to be 0, because the point is, the moment I cross the boundary, it has to be positive, it has to be strictly positive. So, if I am on the boundary, then this is the last point where I can be 0, after this I have to be positive, right. So, and as long as I am also a member of the initial state, set of initial states, my condition is b at x has to be less than or equal to 0, right. Now, due to the continuity condition, the moment I cross over, I have to be positive, I have, right. So, this is where I will be 0, right. So, now again if we compute the integral, that's essentially b itself, because this is what is the time derivative of b. And this is 0, and this is where I am located at time t, which is inside u. So, this is positive, right. Now, you see this again is contradicting the third condition, because what we are integrating is negative, right. So, if we are integrating something negative entirely, right, then it cannot be this I mean the integration output cannot be negative, like I mean it cannot be positive here, right. Since this thing is less than or equal to 0, right, for all x belonging to my domain here, right. So, the state trajectory also could not have gone to unsafe. So, in any way we are trying to do it, we are getting a contradiction. So, that means this theorem must be true, that well, if those conditions happen, then the system must not be able to go to an unsafe state. And I believe it has been very clear right from the outset, right. If you just look at the theorem, you can always intuitively claim that we have the function to be negative or equal to 0, and if I get inside the state space of unsafe region, we must be fully positive, strictly positive. Now, if initially I am 0 or negative and my time derivative says that I can only decrease, then anyway I cannot ever get inside this unsafe region, right. So, that's about the proof. It is as simple, intuitive as that. So, fine. What is the usefulness of this? So, this provides you a sufficient condition, and one can check the safety concern of a control system if by figuring out a various certificate. However, if you cannot figure out a certificate, you cannot draw a conclusion like this, but I mean, so this is I mean, as long as you can figure out this certificate, you are fine. That is a sufficient condition. So, but the issue is how easy is finding that certificate? It can be challenging, okay. But there exist efficient numerical techniques for findings and certificates. That means you can guess a polynomial, and you can give that polynomial all these constraints of various certificate and ask a solver to solve this for you. It may or may not be possible for the solver, because so there exist these efficient numerical methods for certain forms of certificates, like this polynomial fitting, okay. So, you create a polynomial form with unknown coefficients, and you ask a solver to figure out what should be the coefficients of the polynomial, so that all these conditions get satisfied, and so that may be possible in that way, okay. Now, these are some advantages with respect to SMT and other techniques, because these are deductive method. If you can have this function synthesized, then you can just directly say that you are safe, okay. So, here let us take this example. So, you have a continuous time dynamics like this, and let us say your initial region is I mean this is your domain. So, is the positive I mean quadrant with x and x1 and x2 both being 0 in the greater than or equal to 0 in the phase plane, okay. And you have an initial region. The initial region says that well the value of x1 is between 1 and 2. So, this is the initial region, that means that well, and x2 equal to 0. So, this is the initial region marked in blue. So, x2 equal to 0, that means you can be starting at any of the points on this line, starting from this point 1 and ending at 2, okay. And you have an unsafe region. So, unsafe region specification is using this triangular form, because it is an intersection of three linear equations. Each equation will give you one line here, right, linear inequations. So, x1 less than equal to 2. So, x1 less than equal to 2 is what? So, that means x2 can be anything. So, you have this line, that means anything, because if you go beyond this x 1 is greater than equal to 2. So, everywhere inside this line, and then x 2 less than equal to 2, then everywhere on this side of this line, which, so this is your, if I just mark them for you, x 1 less equals 2, this is x 2 less equals 2, and the other one is this line x 1 plus x 2 greater than 3, because if you are on this side of the region, you will have x 1 plus x 2 less than equal to 3. So, they together give you this triangular shape, and this is, let us say, your unsafe region. Okay. So, fine. How do I show that the system is safe or unsafe? Okay. So, let's try and figure out. So, my question is that, well, if I start from anywhere here, is it possible that I get inside this? So, I have to design a function suitably, so that the function, the moment it gets in here, it becomes positive, and in my initial region the function is negative, and the rate of change of the function with respect to time is always negative. So, that is my requirement, right. Now, notice one important thing here. It does not mean that your function should be positive only in the unsafe region. It can be positive at a higher approximation of the at an approximation, an outer approximation of the unsafe region also. Okay. Then, because then all it means that is that it will, you are restricting your system to go beyond not only the unsafe region, but, so what I am meaning is that, let us say I do not get a function which is exactly positive here, but I mean which is exactly positive here and it is negative everywhere else, but maybe I get a function which is positive in this region, and apart from this region everywhere it is negative. Suppose I design that function. Is that a proof that my system is safe? Definitely yes, right, because then again I am able to show that, well, I have this function, once I can figure out a function which is positive here and negative everywhere else along with other conditions, that means my system can start in the initial region and it will never reach anywhere inside this, and since it will never reach anywhere inside this, it will also not reach anywhere inside this, right. So, that is how we are defining the certificate then. My point is, it need not be that I am only positive in the unsafe region, I can be at a bigger region also which contains the unsafe region. So, with this idea in mind, let us create a barrier function which is something like this. But well, if I take something like this, what is my value at 1 1? Well, it is fine. Am I positive somewhere? Let us see. What I want is anywhere in my initial region I have to be negative, right. So, my question is B x has to be negative at least in the initial region, which is this, right. So, that means if I have x, this is my x 1. So, x 1 can be 2, right. So, even with x 1 equal to 2, I will have this as 4, right, but I still need to be negative. So, let us say I make it something like 4.4, something like that, right. So, you see what happens, what is the nature of this function. Then if I take my initial region which starts from 1 comma 0, x 1 comma x 2 up to 2 comma 0, the max value is 4, right, and so that means Bx is negative everywhere here. Where else is Bx negative? That is the important question. So we can see that Bx will be negative in this entire circle if I just extend it like this with this radius, right, because if you see this is like a equation of a circle, right. So what I have is x1 square plus x2 square. I mean as long as I draw a circle with radius 4.4, everywhere inside this it will be negative, on the circle it will be 0, and outside the circle it will be positive, right. So that's what is happening. So on the circle I will have this equal to 4.4, inside this it's negative and outside it is positive, right. So so that's about it. Now I can show that this function Bx equal to x1 square plus x2 square minus 4.4 is negative for all the initial states, which is true, right, because if you put the value, the max is 4, right, it's negative. And if you now take Bx's value here, I mean and technically like I said that if I just take this segment here, this is the segment where it will be negative in the state space, and outside this circumference here it will be positive, right. Now let us check the other condition, which is del b del x times f x. So by the way, these systems this was the system's dynamics. Let me write it here again. This was my system dynamics, right, and so if you just use, so this is your x dot, right, and if you take del b del x, then it is 2x1 plus 2x2 . Sorry, that is so when I am taking it, it is basically a partial derivative, right. So it will have two components, right. So it will be in the first component when I take del b del x1, so that is 2x1 and the rest of it is 0, and when I take del b del x2 it is 2x2, right. So this is it, and x dot and x1 and x2 is also here, right. So if you multiply this here, you get minus x2 in the first row and you get x1 here. So overall what you get is minus 2 x1 x2 plus 2 x2 x1. So that's minus x1 x2. Okay. Yeah, sorry. If I look at the last line, yeah. So they are actually cancelling each other. So this is 0. So if we see the derivative is 0 for all states. Now if we look at our condition, which is our requirement, so the derivative of b with respect to time, which is del b del x times f x, can be less than or equal to 0, right. So if it is equal to 0, that's fine. So that means there is no change in the barrier function's value over time, that's all it means, right. So then as we can see that if I choose my barrier function like this, sorry, yeah, if I choose my barrier function as something like this, I get this kind of a circular region inside which I have my set of initial states, and this is negative or equal to 0, this is negative actually here, and beyond the circular region it is positive, and this beyond the circular region I have a subset which is my set of unsafe states. So, definitely here also it is positive, and the rate of change of this function is 0. That means, this barrier which is right now negative everywhere inside is never going to be positive, because the rate of change is 0, right. I mean, it is not never going to change anywhere. So, then it is fine, we can actually say that well this does not change. That means, the system dynamics that we define is such that I have a formal guarantee that this system is never going to reach that set of unsafe states. So, that is a nice formal technique to talk about stability of such systems. So, with this we will end our discussion here in this week. Only one thing I will like to mention, in our Lyapunov functions and similar formulations, we have talked about these different theorems, but you may observe that everything has been in the continuous time domain. They are all applicable in the discrete time domain also, with some differences. For example, like when I talk about the derivative of the function and we say that it is negative, instead of that we will be writing a difference equation with v x k plus 1 minus v x k. Instead of saying v dot x is negative, we will be saying v x k plus 1 minus v x k. This quantity, the corresponding difference is negative. So, similar theorems also exist for the discrete time Lyapunov functions, and we are not covering them here, but it is just for your information here. Thank you. With this, we will change the lecture here.